Hey there, and welcome to this tutorial for beginners, where we will be talking about Grasshopper and explore why it's such a powerful tool for architects, designers, and engineers. So this tutorial is carefully structured to take you through the fundamentals of Grasshopper, and we'll explore everything from the basics to a bit more advanced techniques, allowing you to start integrating Grasshopper within your own design challenges. And Grasshopper is really a tool that rewards experimentation, so try to experiment as much as you can with the examples and apply what you learn into your own projects, because this will really help you understand how it actually works and how it's all connected. And it will be very beneficial to you later on. So Grasshopper is a visual programming tool that works as a plugin within Rhino 3D. And it's basically a graphical algorithm editor where you build parametric models. So unlike in traditional CAD where you manually create and modify each element, Grasshopper is all about constructing algorithms. So you come up with a set of rules or a logic that allows for the geometry to be created and manipulated within. So this helps you create very complex and customizable designs without actually having to write any code in the conventional sense. And because you're working parametrically, you're also able to explore a bunch of different design options by simply adjusting some variables, and you'll instantly get to see the results of those changes. And Grasshopper is also a great tool for automating tasks that would otherwise be very time consuming if you had to make them in traditional CAD. So the purpose of this tutorial is really just to provide you with a solid foundation of what Grasshopper is. And we'll start with the basics and get you comfortable with the interface and how things work, and slowly build up to some more advanced techniques. And that's when you really start to see the true potential of Grasshopper and the power of parametric design. So the tutorial is divided into chapters, so you can always jump between chapters in case there's some aspects of Grasshopper that you're already familiar with. But without any further ado, let's jump to the first chapter and start this tutorial, and I hope you're gonna find it useful and helpful, and thank you for watching. Okay guys, so here we are in my Rhino file, in the Rhino viewport. And in order to start Grasshopper, there's two ways. We can either find it here under Tools and click on Grasshopper, or we simply just type in Grasshopper in the command and press enter. And then Grasshopper opens for us. So this is my Grasshopper viewport, this is my Rhino viewport. This is where I will be working in my script, and this is where I will be able to see the things I'm working on. So everything I do here in my Grasshopper viewport is visualized here in Rhino viewport. And I can choose to increase these and decrease depending on what it is I'm doing. If I'm working on a huge file, for example, in my Grasshopper script, I can increase this. But if I'm only making small adjustments to my script and want to see these visualized, I can increase the Rhino viewport and get a wider angle of what it is I'm doing, for example. So let's keep them at 50-50 for now. And here you see a bunch of different menus. All of these are plugins. So in case you don't have any plugins yet, you might only see up until this menu, I believe. So you will have all these available to you. So here's where you find all your components that you want to place in your Grasshopper scripts. And they are divided into different categories. So you have maths, sets, vectors, curves, surface, mesh, and so on and so on. So when you're new to Grasshopper, it might be a good idea to use these menus because it's easier maybe to navigate to the right component that you're looking for, and you're also able to find all the components that exist with the type of things you're working on. So for example, if I'm working on curves, I can go to the curve submenu, and then I'll find all my curve components here in different submenus. If I hover over something, I'll get to see an explanation of what that component does. So for example, endpoints extract the endpoints of a curve. So if I have a curve and I want the start and end point of that curve, I'll simply place this component in my script and connect my curve, and then I'll get 2 points as the output. So a component always has inputs and outputs, or most of the time. So the inputs kind of define what the output will be. So let's say I want to create a circle. Then I can either go here to curve and find my circle components here, or I can also search for circle by double-clicking anywhere in the canvas and just search for circle, and I'll get a bunch of different components up here with the name circle in it. And if I hover over these, I also get the same explanation as I get in the menus. So for example, this says create a circle defined by base plane and radius. So if I click it, you'll see instantly a circle gets created in my Rhino viewport. And if I hover over these inputs, it says plane, base plane of circle, and radius of circle. And I also get to see what the default value of these inputs are, so what is set at the moment. So this circle is now being constructed in the XY plane, and it has a radius of 1. So if I want to change this, I need to connect new components or parameters to these inputs. So let's say I want to construct this circle in the XZ plane. Then I can simply just search for XZ, and I'll find this XZ plane and connect it to my input, and now you see my circle is constructed in the XZ plane and no longer in the XY plane. Okay, and I can hide the component by right-click on it and click preview, and you see now it's turned a bit grayish. So when something is visible, it's very white, and when it's hidden, it's a bit grayish. I can do this with my circle as well. And if I click enabled, I will disable the whole component, and now the output is no longer giving anything. If it's just this hidden, the output is still giving me the circle, it's just not visualized in my Rhino viewport. So there's a huge difference between something being disabled and something being just hidden. So let's show this circle for now and connect a slider to change the radius, maybe of 50. And now you see instantly my circle increased in size to the because I changed the value of the radius to 50. And if I adjust this slider, you will see it will automatically adjust my circle in real time as I change this slider. If I were to connect a slider with the value of, let's say, 25, and simply just drag this, it will replace the current input that is connected to my component. So by simply just dragging a new input, it will replace the existing connection that there is. I can also choose to disconnect my component by holding Control while dragging my my wire into the component, and then it will disconnect the parameter or the input that is connected. So if I simply just drag it, it will connect. If I hold down Control and drag it, it will disconnect. If I hold down Shift and connect another input, it will add that input to my circle. So now it's creating two circles, one with the value of 71 as a radius and one with the value of 25 as a radius. And depending on which was connected first, the output list will also be ordered in that order. So now you see circle with the radius of 71 and then circle with the radius of 75. If I were to connect this first by just dragging it and replacing the existing connections and then connect this, you'll see the order has changed. So now the circle with 25 as a radius is the first circle. And this will be very important later on when you start to creating more complex scripts, because the order of points or the order of how curves are managed in different lists will have a huge impact on your geometry. Okay, so that is about that. Okay. If I were to connect these to a container, which you don't really make changes to these types of components, you'll find them here, but we'll talk more about them in the next chapter. But you will see that this wire is now has a different appearance than these wires. It's a bit thicker, and that means that it's containing more than just one item of data. So because there are two circles in this data information, this wire is thicker, while these only contain one set of or item of data, so these are just a simple line. If I were to disconnect this, for example, you will see that this wire turns into a single wire as well, because now it's just one item of data in this component. If I were to merge these sliders and then connect it, you will see it's exactly in the same way as it was before. That this is a bit thicker because it has two curves now, and this is a bit thicker because it has two items of data, the two different radiuses. However, if I were to right-click on this and click Graphed, you see that it now turned into a zigzag wire, and this means it contains a bit more complex data that is organized in a data tree structure. And we will definitely get more into this in later chapters, but for now all you need to know is that this means that it's a set of data that is a bit more complex. If I were to flatten this, it will turn this into a single list of data again. But more about this in later chapters. Now all you need to know is just the difference in how these wires can be visualized and what it means. So this means that it contains a more complex set of data, basically. If I were to graft this as well, they would kind of take out each other, so now it's not as complex anymore, but as I said, we'll talk more about this in later chapters. So let's group these. This is another very important thing to know, that you can select all of these and right-click and make them a group, and then you can set a color to them. You can make them into blob outlines or rectangle outlines, and organize your script visually in order to make it more clear what it is you're doing. Because when you have a huge script with a lot of different components, it will get very messy unless you have some type of structure to it. So one way of making this structure or keeping it organized is to group things that are related to each other. And you can also use a component called scribble, and with this you can write small notes that will help you know what this part of the script is doing. And you can add this to the group, for example. So let's hide all these for now, and let's talk a little bit about how we get error messages in Grasshopper. Oh, I forgot to say, you can also, if you right click on this curve, you can choose to bake it, and that means you export it back to Rhino. So right now you can't really click on these things in Rhino, they only exist in Grasshopper. But if you right click and select bake, you can choose in which layer you want to export these curves into, and then click OK, and now you will see that they exist in Rhino as well. And then you can continue working on them in Rhino. Okay, so let's hide all these for now. We will talk more about how you import things from Rhino to Grasshopper in the next chapter, but this is all for now. So let's say we have a division component here, and we'll connect a slider with the value of 50 to it. Now you see that it's orange, and that is because it's not really working in the way that it's supposed to work. So if I hover over this message, I'll see input parameter B failed to collect data because no slider is connected to here. So the output is just empty generic data parameter. It's not doing what it's supposed to be doing. So when something is orange, it means that you need to fix it, or it's not exactly working as it should be working. In many times, orange means that you're still able to. It doesn't necessarily mean that nothing is working as it should. Like many times you are able to continue working on your script if you get an orange message. In this specific case, you wouldn't be able to continue working because it's not generating any type of data as its output. But if I were to connect the slider here, it will of course turn white, and now it's working as it should. So orange just means go back and see what is wrong because it's not exactly doing as it should be doing. But if I were to have, let's say, a mesh container here and connect a slider to this, it will turn red because a mesh container can only contain data that are meshes. So when I connect a slider, it says data conversion failed from number to mesh, and the output is just null, nothing. So when something is red, it means that this doesn't work at all. You need to go back and make changes to your script and find what it is that's not working, because your script will not function at all when something is red. So that's the difference between orange and red. And yeah, we'll talk more about components and parameters in the next chapter. But for now, I think that's about it. Just a small introduction into the Grasshopper interface in the viewport, and let's jump to the next chapter. Okay guys, so in this chapter we're going to dive deeper into two fundamental concepts of Grasshopper, which are components and parameters. So components are the building blocks of any parametric model. You can think of them as the functional units that perform specific tasks, whether that's creating geometry or adjusting a shape or modifying data. And they usually have inputs and outputs. And the parameters are the variables that feed data into the components. So let's have a look at some of the basic ones here. I've already talked a bit about these containers, and they are components that you can't really make changes to. They just contain a bunch of data. So how we usually use them is when we want to reference something in Rhino inside of Grasshopper. So if we have a curve in Rhino that we want to keep on working on in Grasshopper, we'll simply select our curve and put right click on the curve container, and then we'll select set one curve. If we have several curves that we want to work with, then we'll select both of them. And it's important which order we select them, because they will be organized in that order. And then we'll right click and we'll select set multiple curves. And now both of those curves are referenced in this component. And this can be done with surfaces or meshes or points or anything. We also have containers containing other types of data than geometry, like Boolean values or text or integers or domains. But we're not gonna be talking so much more about that, because that's not something you're probably gonna use a lot in the beginning. But these containers can also be very useful if you want to keep your script clean and organized. So you can, if I have, let's say, a circle here with a radius of 50, and I want to continue working on this circle but in a different part of my script, then I can just connect it to this container and drag this container to that part of the script and continue working on it there. So I don't have to drag the whole thing, or if there's a bunch of different components here working together, then I don't have to mess that organization up by dragging something from there. I can just drag it to a container and then just drag the container to the part where I want to keep on working with it. But I hope that makes sense to you. But yeah. So let's delete these two curves as well. Here under input we have some very important things. We have the number slider, which we've talked a bit about before. If you select the number slider from the menu, you'll simply get a slider with the default value of 0.250, and it will go from 0 to 1. So if you want to change those values, you simply double click on it and you put in the minimum value that you want. Let's say we still want 0, but we want a maximum value of 100. Then now we have a slider from 0 to 100. And if we don't want 3 decimals, we can also change that here by simply dragging this slider. So if we don't want any decimals at all, we can drag it to 0. And now we don't have any decimals at all. We can also change it into an integer, or if we just want even numbers or even odd numbers, we can change that as well up here. So let's say we want 1 decimal. We want the maximum value to be 50 and the minimum to be minus 50. Okay, but one easier way to get this number slider is to simply just double click anywhere in your canvas and just put a number, and then you'll get a slider with the default value of that number that you just put in. If you put the number from 0 to 10, or no, from 2 to 10, you'll get a slider from 0 to 10. If you put something from 0 to 1, if you just put like 0.5, then you'll get the minimum value of 0 and the maximum value of 1. If you put anything over 10 but below 100, you'll get the minimum value of 0 and the maximum value of 100. But if you want to have specific sliders, let's say you want a slider with the minimum value of 55 and the maximum value of 160, then you'll simply put 55.160 and you'll get the slider with those values. But if you want decimals, then you also have to put them in. So you put, let's say you want the same slider, but you want 3 decimals. So you put 55.000.160 or whatever it was I had before. So now you'll get 3 decimals into the same slider. And you only have to put the number of decimals in one of the values. So you don't have to put 55.000.160.000. You can only put the number of decimals in one of the values, and you'll still get those decimals in your slider. So I hope that makes sense to you guys. Let's delete all these sliders. We also have something called a panel, which is a great way to kind of check on the information that your components are feeding out in a very fast forward way. So let's say I have a series component here, and I want to know what is this series component giving me right now. I'll just drag it to the panel and I can see, okay, it's giving me now 10 different values from 0 to 9. But it can also, a panel can also be used to feed in data. So if I just simply put 56 here and connect it to a circle component, then I'll get a circle with the radius of 56. You will probably use a slider if you want to create that circle, but it's important to know that the panel can be used in this way as well. And if you want, let's say you want 5 circles with different values, and you want the values to be specific values, like you want 56, 25, 35, 69, 69, and 90. Then now you see the component turned red, and that's because the default state of a panel is that it can only give you one value. So now all these numbers are still treated as one value, but it's kind of an incorrect value because I put they're not yeah, connected into one number. So if you want it to be treated as different values, you have to right click on the panel and select multi-line data, and it will transfer these values into several lines of data. So the circle component can read it as different types of radiuses. So it creates now circles, one circle for each number that represents the radius for that circle. I hope that is clear for you guys. We also have a Boolean toggle that can be either true or false. You just double click it and it gives it an either true or false value. So let's say or wait, let's make an example here. So we select the series to a panel and we see, okay, now it has 10 different values from 0 to 9. If we have a cool pattern, which means that you can remove items in a list depending on if you feed it a true or a false value, and we connect this to the list, and we connect our toggle, our Boolean toggle, to the here, and then we'll see what happens to what it feeds out. Okay, true. No. And if we put it to false, it will remove all the items here. But if we, let's say we make, now you see something happened here. What happened here? Yeah, it removed a certain number of values, and if we hover over the culling pattern, that's the default pattern in this component, you'll see that the default value is false, false, true, true, which means that the first two values will be removed, and then the second two values will move forward, and then it kind of repeats this pattern. So the next two will be removed, and then the next two will be allowed to to go through. So by doing so, you see that this list now only has 4 values left, because 6 of them were removed because of this pattern. And here is also a great way how we can use this panel as a multi-line data by giving it different types of true and false values. So if we give it true, false, 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 true, false, false, and we do have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now we have 10 different true or false value, and we feed this into the culling pattern. You see that we only have 4 different true values in this list, and therefore we only have 4 different values that are moving on forward as the output from this culling pattern component. I hope that makes sense to you guys. And let's see if we have something else here important. We have the MD's multi-dimensional slider, which can be used to, if we make a quick surface here, and then we reference it into our script, internalize it, and then we can delete it. And then we use a component called evaluate surface, and we connect our UV coordinate that we get from the multi-dimensional slider into here, and we reparameterize the surface and connect it to the surface input. And now you can see from this component we get something, an output that's called a point. So we can simply connect this to the point, and then we can hide these two. Or we can keep this, by the way. And now you see, depending on where we have this point in the multi-dimensional slider, we get a point on the surface that represents that location of the slider. So this can be useful in many different ways and in many different scenarios that we're probably going to get to later. Let's see what else we have here that's important. Yeah, we have the graph mapper. We'll talk much more about that later, where we can use different graphs to achieve different types of values. And here we also have something called scribble, which is good for organizing your script. So you simply it's just a text that you can have to tell yourself what this part of the script is doing. So let's put something like components here. We also have something called gene pool, which is basically a bunch of different sliders that you connect to Galapagos in order to optimize your design according to whatever you want to achieve. But that's pretty advanced, so we're not going to talk more about that now, maybe later. Let's see, we have some component called range. And what that does is it gives us a range, so we feed it a domain and a number of steps. So first we need a domain, so we need the component called construct domain. And what that does is it gives us a domain based on what we feed it as an A and a B value. So we'll connect it to two different sliders. We'll put one at 0 and one at 100. So if we hover over it now, we see that this is a numeric domain between 0 to 100. So we'll connect this to the range domain, and then we also need to connect a number of steps. Its default value is 10, so let's add 10 more and make it 20. And now let's see what it's actually feeding out to us with the help of a slider. So it's giving us 20 values between 0 and 100. So if I change this value, it will automatically change the number of values that it's feeding out. And if I change this, we will get less values, but still with the same domain. So if we have from 0 to 100 with 10 steps, then we'll get each step will be 10, basically. So that's about that. And we're gonna talk more about the different types of components and parameters along the way as we are using them. But for now, I think this was an overview that I hope makes sense to you, and that gives you an idea of how components and parameters work together in order to create something for you. Okay, let's go to the next chapter. Okay guys, so in this chapter we're going to take it the next step into the world of Grasshopper, and specifically how to create and manipulate basic geometry forms like points, lines, curves, and surfaces. So in traditional CAD creating geometries, it often involves manually drawing and adjusting each shape, but Grasshopper really allows us to define geometry through a set of rules and parameters. And this is where parametric design truly shines, because it allows us to create very flexible models that can adapt to a wide range of inputs. So in this chapter, we're going to focus on building very basic geometric elements, starting with simple points and lines, and then moving on to a bit more complex shapes like surfaces and curves, or curves and surfaces. So we're going to explore how to use sliders and other controls to dynamically adjust these shapes, giving you a really hands-on introduction into the power of parametric design. So let's get started and dive into creating some geometry into Grasshopper. So we are here at the vector submenu. We have a category called points, and here we can select a component called construct point. And what this does, it creates a point. And the default value on all the coordinates are 0, 0, 0. So this point is placed in the 0, 0, 0. So we're gonna copy this point and create two sliders going from 200 or minus 200 to 200, and set the default value at 0. and copy it into two versions so we can adjust this second point. We're gonna leave the Z value for now because we want it to be in planar, just to keep it a bit more simple for now. So let's adjust this point and move it around a bit. So here we have our first point up here, you see, and then our second point up here. So if we go to curve and under primitive, we can find a component called line. And if we hover over it, it says creating a line between 2 points. And this is exactly what we want to do. So we'll place it here in our canvas and connect the 2 points we just created. And now you see we have created our first line. We can also, just to show you how we can take advantage of the panels that I talked about before, we can connect this line into a length component that measures the length of the curve that we put into it, and then we'll connect that output into a panel. So we'll get the length in this panel of our line. So if I adjust the position of our second point, you can see that the length of our line is shown here. So for example, if I want to create a line that's 200 meters, I can adjust my inputs into my point in order to achieve that. So here is our first line. So we're gonna create a group out of this and hide it for now. Let's copy our points to create something different. And we're gonna copy this second point one more time, so we have 3 points. Let's put the preview on for now. Okay, so here we have point 1, point 2, point 3. And what we can do with these ones, if we go back to curve and primitive, we have something called circle 3 point. So what it needs is an A point, a B point, and a C point. So we're just going to connect our 3 points into it and see what happens. And it creates a circle based on these points. So if we move around the position of these points, you can see how the circle adapts to where the position of our points are located. And we can do the same thing as we did with our line, but we can connect it to an area component that will measure the area of our circle. And we're going to connect it to a panel. And now you see how we move around the position of our points. You can see that the area of our circle also dynamically changes. So that's pretty cool. Let's group it and hide it for now. And let's copy these 3 points and see if there's something else we can create out of 3 points. And here we have something called arc 3 point. So let's put that into our canvas, and once again we're going to show our points. And now we created an arc. But let's keep the x at 0, the y at positive, and this x at 0 as well. And then we're gonna add a z value instead, so we can create a really nice looking arc. So here we have our arc. And if we move the first and the second point closer, you see it turns into a more circular shape. But if we drag it out, it gets more into an arc. So this component is really useful if you want to create a nice looking arc structure, for example. So let's group it and hide it for now. And yeah, we can also create a rectangle by putting into a domain for the x value and the y value if we want to do that. But then we need 2 different domains, so we're gonna add construct domain component and copy it, and let's put a negative, two negative parameters there, and then put a slider, let's say 20 as a default value. We're connecting it to the negative, and then the negative to the A, and our slider to the B, and we're gonna do the same with the Y domain. And we're connecting the domains to X, to Y, and here we have our rectangle. We want it to be in the XY plane, which it is in default, but let's just make it clear for now. So here is our rectangle, and if we change these values, you see that our rectangle also changes dynamically. So that's how you create a rectangle. If we want to create something more irregular, like a curve that's not a line but a bit more organic, let's see what we can do. Let's copy these three. Let's disconnect the Z value. Copy it again. So we have 4 different points, and let's put the preview on for them. And let's make it a bit more irregular. And here under spline we have a component called interpolate curve. So let's see what happens if we connect our points. So this is point A, point B, point C, and point D. And we'll get this nice organic curve going through all of these points. So if we change the position of the points, you also see the shape of the curve. It changes dynamically. We also have something called a NURBS curve, and that will create a curve, but not in the same sense. It will use these points as control points rather than as points to go through. So if we compare it to the interpolated curve, you see that the NURBS curve goes somewhere in between them. And if we adjust the position of the curve, you see the change in the NURBS curve is not as clear because it only uses the curve as a control point of it, of the shape. So, however, if we change the degree, now the default is set to 3, but if we put a slider 1, 2, 3, and change the degree to 1, you're going to see that both of the curves turn into these straight curves. If we change to 2, you see the NURBS curve kind of changes along with that, and if we change to 3, the interpolated curve also changes. We also have something called offset curve. So if we're gonna hide the NURBS curve for now, or let's hide the interpolated curve because the NURBS curve was a bit more cool. And we're gonna use this component called offset curve. Oh, I already put it. And what it needs is an offset distance. So we need a slider to give it that offset distance. So let's put a value of 20 and see what happens. So now we get a curve 20 units away from the original curve. And if we change this value, you see that the curve dynamically adjusts to that value. So if we want to put a value of 16, let's say, to create some a road maybe, we can do that by using the offset curve. And there are a bunch of different options here. For once, we can try how we use the fillet option. Let's say we put this degree again to 1 to get a straight curve. Let's hide these. But we don't want this curve to be completely straight. We want to smoothen the corners a bit. Well, then we can use a component called fillet. or there's a bunch of different components that does this for you, but let's use the fillet distance. And it needs a curve, so we put our curve into it, and it needs a distance from corner of fillet start. And what you see it does is it kind of smoothens out the straight corners, the hard corners a bit. So if we increase this, you're gonna see an even more smooth out corner. So this is a bit about curves. Let's see if we have these two curves. Let's change it back to a degree of 3. And we have these two curves. We have our NURBS curve and the offset of our NURBS curve. Then we can also use a component called tween curve, which will give us the curve in between these two curves. So we connect one of them to the A, the second one to the B, and because the tween factor currently is set to 0.5, we get the curve that goes in between these two curves. But we can also connect a range, for example, to this value, and the default value is from 0 to 1, so that fits us perfectly. And the number of steps is 10. So if we connect it, let's see what happens. And it kind of creates 11 different curves, because the range of numbers are 11, going from 0 to 1. And we get then 11 curves from the first one to the second one. And this tool is very, very useful for many reasons. And then we can manipulate these curves in different ways, how we want. So let's hide that for now and put everything in a group. And drag it up a bit. And I think that's about what we do. Yeah, we're gonna get to more of these components later on, but for now I think this was the introduction that you need to how curves work and how it's connected to points. So let's move on to surfaces. So surfaces can be made in several different ways. So let's say we have these two curves, for example, and we want to create a surface in between them. Then the easiest way would be to use a component called ruled surface, because it needs two curves and it will create a surface between those two curves. So if we drag these two and to A and B, it will create a surface between those two curves, basically. And if we then change the position of our originally curve, you can see that the surface dynamically adjusts to those changes. So that's pretty cool. And let's say we have a third curve. So this will make this group a group. This one. Okay, so we have curve 1, curve 2, and curve 3. Let's merge them. So we have curve 1, curve 2, and curve 3. Let's just flatten them out to be sure everything works right. And we're gonna turn everything else off. So if we want to create a surface out of 3 curves, then we need to use a component that's called loft. You'll find it here. Create a lofted surface through a set of section curves. And yeah, voila. Not prettiest curve because, or the prettiest surface, because the curves are a bit weird. But yeah, this is how you create a curve through a series of, or through a set of curves. How you create a surface through a set of curves. And here we can also add a z value just to see, to get a bit more of an organic shape into our curve. So now this point is up in the air, and therefore our surface is now going up in the air. Let's look into other ways of creating surfaces from curves. There's one component called extrude. So if we take one of the original curves, for example this nerves curve, or maybe we'll take the offset version of it, and we want to just extrude this in one direction, then extrude is the component that we're going to use. And we just need to plug in a unit or a direction to this input, and then we need a slider to control how much we want to extrude our curve into that direction. So I connect a value of 50 to my z unit component or parameter, and then I connect that to the distance for my extrusion. And now you can see I can control this extrusion by adjusting this slider. So if I drag it up to 100, my curve will extrude 100 up in the set value. So that is extrusion, but we can also extrude to a point, for example, or extrude along a curve. But let's check the extrude to a point. So if we're gonna instead extrude to a point, let's move this curve the same distance that I just extruded it. So by dragging the unit to the transformation or the translation vector in my move component, and then I'll put my curve into the move, the curve will move in the same distance as I just extruded it. So let's hide this extrusion for now. And then I need to get a point from this curve. So then I can use a component called point on curve. And what this does is it gives me a point based from this curve. So the default is set at 0.5, which is right in the middle of it, but I can change it. And then I can use a component called extrude to point. And I use this point, connect it to the point input, and I have my originally curve down here, and drag it to the curve input here. And you see it creates an extrusion to that point. And if I change the position of my point, you can see that the extrusion also adjusts to where that point is located. Let's keep it at mid for now and hide it and see what else we have here. We have something called boundary surface, which is basically just creating a surface from a closed curve. So I need to put the periodic curve Boolean value into true and make it a periodic planar curve. I also might want to just create a completely new curve, because now it's all a bit weird. So let's create this. And let's disconnect this. Okay, so here's my curve, and I'm gonna hide everything else for now. Okay, so now I have this interpolated curve here, and I'm gonna set this value to true to make it closed, and just connect it to boundary surface. and it will create a surface based on that curve. If I change one of these z values to anything other than 0, you're gonna see that it won't create my surface anymore, because this requires the curve to be planar. What I need to do then is to use the component called patch surface, and there it will create a surface based on my curve. Okay. So let's remove this for now, and let's hide those. Set the Boolean value to false. And now I want to show you how we can make something called a revolution curve. So what the revolution curve is basically you need a profile curve and you need an axis curve, and then it will rotate around the axis curve and create a surface based on that, which is great if you want to design a vase or anything like that. So here we have my profile curve. I just need to create an axis curve. So I need the first point and the second point, but I need the second point to be with this value of 0 in the x-axis, so it becomes a straight line. And I'll create a line based on those curves and use that as my axis curve, and use the originally curve as the profile curve, and boom, here we have my base. What the D wants is it wants a degree or an angle basically, but the default value is set, even though it's set in radians here, but it's set to 360, so it will create my base for me without having to change that value. So let's hide that for now. Let's hide everything except my curve, and move my curve down here. One other way we can create a curve surface is with our sweep. Or first, let's just see. Pipe is a very easy way to create a curve. We just need to put a radius basically and connect our curve to it, and it will create exactly what the name is, a piped surface around that curve. And if I change this value, you can see it increases the radius of the pipe. So let's delete that for now and use my sweep component. For that I need to have a railing curve, which is this, and I also need a section curve. And for my section curve, I need to first create a perpendicular frame out of my railing curve. And let's put numbers segments to 1, and then I'm gonna choose one of them with my list item component, and on this plane I'm gonna just create some form of simple curve, let's say an ellipse. Okay, so now I have an ellipse placed on my plane, and I'm just going to use this ellipse as my section curve, and the railing curve, as I told you before, will be this one. And what it does is it will basically drag this curve along the railing curve and create a surface based on that. So those are some of the ways you can create curves based on, or create surfaces based on curves. And we will definitely get more into it later on in the video, but this was a brief overview over how points, curves, and surfaces are all connected. So. Hey guys, so in this chapter we are going to dive into one of the most crucial aspects of Grasshopper, and that is data management and lists. And in order to understand how Grasshopper works, it's really crucial to understand how we work with lists. So without any further ado, let's jump into it and let's check out our script here. So under here we have a subcategory called sets, and under this category we have something called list. And we're gonna try to explore a bunch of these components and see what they do and how we can use them. But in order to do so, we first need to start by just creating a simple list. So let's use a series component to do that, and let's connect a panel to it to see what type of information it's giving us. So the default value for a series will give us a series starting at 0, because if you hover over here it will say first number in the series is 0. Step size for each successive number is 1. So every index the value will increase with 1. A number of values in the series is set to 10, so we get 10 values from 0 to 9. So if we want to visualize this data in our Rhino viewport as well, we can connect it to a construct point component and connect it to the Y input, for example. And now we have these values as points in our Rhino viewport. Let's say we want to create a completely random set of numbers. So we'll use a random component for that. We also connect a panel to it to see what it's feeding us. The default value is only feeding us one number, so let's change this number of random values to 10 like we had in our series. And let's change the domain of the random numbers to 0 to 20. Before we used the construct domain component to set our domains, but we can also always just right click on the component itself and set it within the component. It's a bit faster, and if we know we don't want to change this domain later on, then it's probably a better way to just set it right in the component itself. So we connect it as well to a construct point component in the y-axis, and then we'll use something called list item. And what a list item component does is it selects one item in a list for us. So we need to plug in a list and we need to plug in an index. So let's put a slider 0 to 9 into our index input. And now you see, if we hide the random point lists for now, you see we can select one specific point in this list. By simply adjusting this slider, we will select a different point. And as you can see, these lists are all organized in the order that they appear in the y-axis. So the last item is the last one to appear in the y-axis. If we want to apply the same logic to a random list, because if we connect it now to our random lists of points and we hide this, you see that these lists, they just appear in a completely random order. And let's say we want to have the same type of logic. So we want the item index 0 to be the first point that appears in the y-axis. Then we can use a component called sort list. And then we connect these values to the key input, and it will sort these values for us, starting with the smallest and ending with the largest number. And if we want to sort the points accordingly to the same type of logic, then we just plug this into the A input, and the A output will be our points sorted in the same logic. So if we connect it to a point container here, for example, now these points should appear in the same order as these points did. Like the first item should be the one that appears first in the y-axis. So let's hide these for now. And now you see that we can select them in the order that they appear in the y-axis. So this is what sort list does for us. It's a very powerful tool. You can sort it based on anything from area to length to distance to something. So it's really useful in many different types of scenarios. So let's hide that for now and check something else here. We have one component called list length, which basically just measures how long a list is. So if we connect our points to this, it will give us a value of number of items in list is 10. We also have something called reversed list. So if we connect our points to this and then choose our items, now you see it will start with the highest value. So it will start with the point that appears last in the y-axis. So it basically just reversed the list for us, as it says. We have something called shift list, which is let's say we want to create we will create a fast curve here based on our first points that we did, and then we offset this curve with a distance of 5. Now we have two curves here, as you can see, and we will divide both of these curves into numbers, into points. So we'll divide them into 10 points. And then we'll connect these points with a line component. Now you see that we have created lines between these points. Let's say we want to make some type of pattern where the lines that we create are a bit more diagonal, so they are not as straight as they are right now. Then we can use a component called shift list, and what this does is that it's basically moving everything as much as we want. So if we connect our list here to the L input, and here we can select a shift offset. So we'll make a slider from 0 to, let's say, 6, connect it, and then we connect the output into our line. So because the shift list is now at 0, it doesn't do anything for us. But if we increase this, you see that then the point that will connect to these points are all shifted one step, if that makes sense. We can also wrap this value if we don't want these extra long lines, because it will start over from the beginning. So these points now that have been shifted, they start over here. So the index of this point is the same index as the point of this in this list, if that makes sense. We can make this wrap value to a false, and it will not create those lines, but instead it will create, because one of the lists is longer than the other, so these points that don't have a point to match with, they will automatically match with the last point. So if we don't want that, we can also use something called shortest list, which will shorten both of the list to the because this list has 9 items, while this has 11 items. So if you connect them both to A and B, the output will be 2 lists with 9 items each, and we connect them to the line input, and now you see we only have those lines that we want. And this can also be done with a component called longest list, but it will do exactly what that says. It will increase both of the list to the longest list that is in the input. So that's shortest list, longest list, and shift list for you. Let's hide all that for now and see what else we have here. We have something called sublist. So let's say let's copy this point component that we made before. And let's say we want to choose some specific points in this list and manipulate only those points. We don't want to manipulate all of the list, all of the points. Then we can create a construct domain component and connect that to, first we'll have to create sliders to it. Let's set them from 2 to 5 maybe, and connect it to the domain input, and we connect our points to the list input. And now you see we select those points that we have as the domain. So if I have the domain starts at 0, it will choose the points from 0 to 5, and we can change that with our domain. So let's say we want to choose the point 5 and 6. And we want to move them, or let's say we choose 4 to 6. And we want to move them a bit in the z-axis. So we'll connect, we'll use a move component and a z-unit parameter, and we'll connect a slider to that, and move them 5 units up in the air in the z-unit. And now if we want to put these points back into our original list, we can use something called replace items. And we'll plug in our original list in the list input. And here it says if items to replace with, and those are the items that we just moved. And here it says index, replacement index for each item. And here in the subset component, we also get an output of those indexes or indices. So if you plug that in, it will create a new list for us with the moved points that we constructed before. And here we can now select more of them. We can hide everything, and we only have the new list with the moved manipulated points within them. And now we can connect this to, let's say, an interpolate curve component, and we'll have this curve that we can manipulate with our components by adjusting our variables. Maybe move it a bit less. Okay. So this is how we can use the subset component. We also have something called weave, where we give this component a pattern. If we have 2 different lists, let's say we have the random numbers and the numbers we got from the series. Or no, let's use these instead. It's a better example. So before we offsetted our curve and divided it into 10 points. So we have 2 lists of points here. Let's plug them into containers to make it a bit more clear. And we'll move this a bit further away. So we have this list and we have this list. And now we want to create a list with informations from both of them. So here we can give this component a pattern of how we want to combine these lists together. So we'll plug this into 0 and we'll plug this into 1. And the default value is that this will weave a list. First it will take 1 item from the list that we plugged into 0, and then it will take 1 item from the list that we plugged into 1. So it will create a list basically of 22 points where they will be 1 point from this, 1 point from this, 1 point from this, 1 point from this. So if we connect this to an interpolated curve now, you're gonna see that it creates a list for us that goes in between these lists we had in the beginning. Or it will create a curve for us that takes advantage of both of these lists of points. So this is how you use a weave component. Let's hide that for now. Let's see. Let's check out cross-reference. What cross-reference does, it matches every item in the A input with every item in the B input. So let's say, for example, we have a series and we connect it to a unit Y component. And then we connect the same series to a X unit component. And then we connect the Y units to the A and the X units to the B. So if you hover over, you can see that the A input has 10 values and the B input has 10 values. If we hover over the output, it will give us 100 values in the A output and 100 values in the B output. And if we connect those values to a construct point, you see that we now have a complete grid of points, because every unit in the Y will match with every unit in the X. So it creates 100 points for us in this way. And this is a very strong and useful component. It can be used in a lot of different ways. For example, let's say I have a circle and let's put the radius to 50. Let's put our output into a curve and hide it. Let's hide what we did before here. Okay, so here's my curve. I want to divide it by a bunch of points, into a bunch of points. Let's say I want to have 30 points. And then I'll use a cross-reference for these points. And then I'll use a line component and connect A to B. And what you see now is that every point in this circle that I divided will connect and create a line to every other point. So now I get this really cool pattern, which I can adjust by simply decrease or increase the number of points that my circle is divided to, which is pretty cool. And then I can use something called, if I want to continue working on this, I can use something called, or I can cull items in this list based on specific criteria. So let's say I only want the curves that has a certain length to it. So let's measure the length of all of these curves or these lines, and let's use a smaller than component to cull the items that are not long enough for me. So I connect the length to the A, and then I connect a slider to the B, where I will choose the value that I want the lines to be longer than. And then I'll use a component called cull pattern, which I've shown before, because what this does is it gives us a value. If A is smaller than B, it will give us a true value, and if it's not, it will give us a false value. So I connect this to the culling pattern, and I connect my list of lines to the list input. And now it's only giving me the lines that are smaller than the number that I feed into this. So let's hide those. And now I can create something like use a point on curve component, an endpoint component to get 3 points, and then I'll use an arc 3 point. Use the start point as the A point, the midpoint as the B point, the end point as the third point. But I'll also want to move the midpoint accordingly to how long the line is. So I'll again use a length component to measure how long it is, and then I'll use a multiplication that I can multiply the length in order to get a z value to create some kind of parametric shape, and I need to connect it to a z unit as well. And I'll move the point in that direction, in the z direction, and I connect the moved point to the second point. And voila, here we have some really weird shape. So yeah, here we have some type of pavilion. And it's giving me a orange message because because some of these are invalid, but we don't have to worry about that now. So yeah, this is how you can use this for one example. Let's see what else we have here. Yeah, in a later chapter we'll talk more about tree structures and how we graph lists and how those things works. It's a bit more complex way of working with trees, but for now I think this is the general overview that you need at this point, just to understand how we can work with lists in different ways, how we can remove data and manipulate data within the lists in order to create whatever we want to achieve. So let's hide everything now, and let's jump to the next chapter. Okay guys, so now it's time to explore another aspect of Grasshopper, which is transformations and modifications. So transformations are really the operations that allow us to change and manipulate our geometry in very powerful ways. So whether you need to move or rotate or scale or array an object, transformations give you this control to modify your objects as you want. And this allows you to create more complex and dynamic forms. So in this chapter we'll start with some fundamental transformations like moving, rotating, and scaling, and then we'll slowly move into a bit more advanced techniques like mirroring and orienting and polar arrays and so on. So by the end of the chapter you'll hopefully have a solid understanding of how to use transformations in Grasshopper. So without any further ado, let's jump into our script, and let's start with constructing a simple curve just to have something to work with. So we'll make the construct point component a slider from -0 to -100 to 100 and put it at 0 as the default. And let's connect them to our point, and let's make 4 of those points, and then connect it to an interpolated curve. And let's move around the point a bit, so we have the z coordinate we can delete actually, because we don't want, we're gonna work in a planar mode here. Wait. Okay, so let's connect the points to our curve. Let's create our curve. Let's set the periodic curve to true, so it becomes closed. Okay, so now we have a curve here. So let's start with the move component. We have kind of used it a bit before, I'm pretty sure, but what a move component needs is a geometry as an input and a translation vector. And a vector can be created by many different ways. We can create a vector by basically doing the same thing as we does with construct point, but instead we construct a vector. So we find that component here called vector xyz. So we'll make a vector with the same types of sliders from -100 to 100 and set the default at 0 and connect it, copy it 3 times and connect it to the xyz. And for a vector to show a vector, there's in our Rhino viewport there's something called vector display. So we'll put this component in here, and it needs an anchor point for preview, which we will put our xy plane for now, and hide and put it there, and then we'll connect the vector to the vector input. And now if we change these values, you will see that an arrow is showing us where our vector is, where this force of our vector is pulling. So if we connect this vector to our translation vector in the move component, and then also connect our interpolated curve that we just created into the geometry, you will see that it moves in that direction. So let's group this and hide it for now, and only show our moved curve. So now we can move this around by adjusting the sliders that control our vector. Okay, so that's how we use the move component. We can also use we can also construct a point. Let's hide this for now. Let's hide the vector display. And we'll use the same values, but we're just going to construct a point to show this example. And now we have this point here. And then we have the original point in the 0, 0, 0. And then we can use a component called vector 2 point, which basically gives us a vector based on 2 points. So we plug in the 0, 0, 0 point into the A input and the point we constructed into the B input. And now we have a vector that basically does the same thing. It translates, it transfers our geometry that that we want to move from the point A to the point B. So if we plug this into the move component instead, it will literally do the same thing as just plugging in the vector. But this can be useful if you have a point already. Let's say you have a circle down here and you get the center point of that circle with an area component, and then you'll use that area component, the center point from that curve as the A, and then the point where you want to move your curve as the B, and you can easily create a vector by using this component. So it's very useful in many scenarios. Okay, so we have our curve. Let's put it in a container down here and hide what we did before. Okay, so there's also something called rotate, which I'm sure you've heard about. We can, to start with, I can show you how we rotate a vector. So this was the vector we created before. And to rotate a vector, we need a rotation axis. So we'll have to move, we need to create a line in the 0, 0, 0 that just goes straight up. So if we connect the construct point with the 0, 0, 0 to a move component, it will move it as a default 10 units in the set value. So we can connect those two to a line, and we will have a line from the 0, 0, 0 that goes straight up. And this can be our, let's make them a group so we know that they are creating our rotation axis for for our rotate vector component. Not enable, preview off. And then we can use the vector that we created before, this one. And here it also needs a rotation angle in radians, but if we change it to degrees, we can use a slider from 0 to 360. And then we connect our, okay, that's already connected, and we want to display this as the new, or as the vector that we display. So we connect the rotated vector into our vector display component. And now if we change the angles, you can see that our vector is rotated along this center point, or the axis that we created before. So it's rotating around this axis. And of course you can create other types of axes if you want to rotate it around that. It doesn't have to be this simple. Just to give you an idea. So let's hide that for now. Let's go to rotation of objects instead. So you can rotate an object by around an axis. So you can rotate an object around an axis. And then you need to the center point of your curve, and you need to do basically the same thing as we did before. Move it up to create your axis. You connect the moved to the B and the other one to the A. We'll make this a group and hide it. And we connect our axis into the X input, rotation axis. And here is the angle, and we'll make that into degrees as we did before. And put the slider from 0 to 360. And then we'll connect our curve into the rotation geometry input. And we hide the original curve. And now you can see we can rotate our curve around itself by just adjusting our slider. We can also rotate geometry around a plane by using this component. So let's say we want to make the default value is the XY plane. We need to change this to degrees as we did before and put the slider into it. And because our curve is already almost placed in the center, so you won't really see a huge difference. But if we change the plane into the XZ plane, you will see that now our curve will rotate in the XZ plane instead. Okay, so these are two different ways you can rotate your geometry, either by rotating it around the plane, or by giving it a specific axis to rotate it around. We also have something called scale. Let's use something else for showing the scale. Let's create a sphere, for example, and give it a radius of 40 units. And if we want to scale this, we need to plug it in, but we also need a center point of the scaling. So we need the center point of our geometry, and we'll plug this into a volume, and we'll get the center point from this component, plug it in. We can hide this, and we'll hide the original, and we also need a scaling factor. So if we want to make it smaller, let's make a slider from 0 to 1. And now we can scale our sphere with our slider by simply adjusting our slider. If we want to scale this, but not in a uniform way, if we want to scale it more in the Z axis, for example, or only in the Z axis and not in the XY axis, then we can use a component called, which was right here under the original scale, called scale NU. And if we hover over it, it says scale an object with non-uniform factors. So it does basically the same thing for us. We need to plug the center point, and we need to plug our geometry, but then we need 3 different sliders. The default value is set to 1 for all of them, but if we plug 3 different sliders in, we can control how much it scales in each direction. So we'll hide the original scale, and then we'll just decrease the scaling factor in the z-axis, and you see now it only scales in the z-axis. If we only want to scale it in the y-axis, we decrease this slider that's connected to that, and you see that it only now scaling in the y-axis. So those are the 2 different ways we can scale an object. Let's jump to array. So we can do something called polar array. Let's use our curve here that we created before. And what we need to plug in is the geometry itself, a polar array plane, the number of elements we want in the array, and the angle. The angle is by default set to 360, so for now we don't really need to change that. It's set in radians, but you can change it to degrees if you want. But we will leave it as it is by now. The number of elements we can control with the slider, and we'll plug in our curve into the geometry. And because the XY plane is fine for now, because that's where it's set almost. So we can adjust the number of elements here by simply dragging this slider up, and you see it creates this interesting pattern, and it basically places our original curve along this center point, or along this plane that we fed into the polar array plane, with the number of elements that we choose. So that's a pretty cool thing. We can also array something along a curve. Then we need a second curve, so let's just copy these things. And let's make this not a closed one. And we'll change. First we need to hide this because it's a bit confusing. And let's make this curve a bit different. Okay. So here's our array curve that we want to array railing curve that we want to array our curve along. So we'll plug that into there. It also wants us to give a number of elements that we want in the array. Let's make it 5 for now, and then we need to plug in the base geometry. So you see now that it follows the curve, but it doesn't actually place the curve along our railing curve. If we want to do that, we first need to move the original base geometry to the starting point of our railing curve. So we can do that with the vector 2 point like we did before. And we just simply need the starting point of our railing curve. So we use this endpoints component, connect it to our railing curve, and we'll plug the starting point into point B and the center point of our curve into point A. So we'll get this vector moving our curve to the starting point of our railing curve, if that makes sense. Okay, so let's hide everything else for now. Wait. And then we will plug the curve that we just moved into the new geometry to array it. So now it's placed on our actual railing curve. Okay, so this is how you array. You can also array linear and rectangular. Let's show linear for now also. It's very straightforward. You just give a direction. You connect the slider to a unit, plug it into the direction, and then you also need to say the number of elements that you want to be in the array. And let's connect our curve into there. And as you see now, it arrays in a straight line in the direction that we gave it. We can increase how strong we want the direction to be and the number of elements that we want by adjusting our sliders. So this is array for you. So we've been through scaling, rotating, arraying. Let's check mirror. So if we use this curve, for example, but let's make the same y values in the first and this last point. So we get a curve that's that starts in the same y values and ends in the same y values. So let's say we want to mirror this curve. If we just plug it in, you see it's not really doing what we want because it's arraying, it's mirroring in the YZ plane. And that's not what we want. We want it to array in the ZX plane. No, that's not what we want. Okay, let's check the endpoints here. Move in the Y unit. So we just need to move one of the starting points in the Y unit to create a line that we can use as our plane. No, I meant the X. Or am I? No. No. Oh, I'm stupid. No, I was doing right from the beginning. I'm just stupid. Okay. So now we gave it a plane based on the starting points or the ending points of our curve, so that we get a nice uniformed mirrored curve from our original curve. So now if we change our curve by adjusting the points that construct our curve, you can see that it now mirrors it, so we can create this very symmetrical shape. Then. So that's, you can create this little heart here. So that's mirroring. We also have something called orient. So if we want to orient something in a certain direction, we need the initial plane of that object. Let's join these two curves that we just mirrored. And then we'll make perpendicular frames from it. And do we have we made some other curve here somewhere? we have a curve here we created before. We'll plug that into a container and drag these things away from everything else to make it a bit more clear. Okay, so let's first of all scale down this curve like we did before. So we need the center point of it, and let's scale it to a factor with a factor of 0.1. Make it pretty small, and we hide those two. So we have this curve here, and it has this plane as its original plane. So we'll plug in this plane as the plane A, initial plane, and then we'll plug in the perpendicular frames that we created from our mirrored curve into the final plane. And then we'll plug our scaled curve into the geometry. And now you see that it will place our curve along these planes that we created from our mirrored curve. So this is how you orient an object in a new direction. And now we can do something like can loft it. We can change it to a closed loft. And now we get this weird little shape of a heart. So yeah, this is how you orient objects. Not delete that, let's hide it. So yeah, we've been through scaling, rotating, arraying, and orienting. And let's just show one quick example of how we can make them all together. So let's go back to here, where we rotated something. So let's say we want to rotate this in several different ways. So we create a series where the starting is 0. The step size, let's create a slider with 20, put it in, and the number of elements, let's put 5 for now. So what it's feeding out now is a series of data from 0 to 80 divided in 5 numbers. So if you plug this into our degree, you will see that it will rotate our original curve 5 times, and every step will be 20 degrees. And we can also connect those to a move component, where we will use the same type of logic, but in the series we will instead we will create a new slider for the stepping, for the step size, and plug this into a Z unit and connect that to the translation vector and connect our rotated circles into it as well. So now you see that we have a set of curves that both are rotating and scaling, and we can adjust the number that we want, and we can adjust how high we want it to go, and we can adjust the scaling and the rotation from between each curve. So if we loft this, for example, you will start to see that we have some type of interesting shape here that we can adjust with our variables by simply dragging them up and down. Maybe we want a really twisted tower, for example, or not as twisted, but we want it to be very, very tall. So yeah, this is how you use rotation and scaling together. And of course, there are a lot of different ways you can do this, and we will definitely talk more about it in later chapters. But I hope this was gave you some type of introduction into how you transform geometries into Grasshopper. So yeah, let's jump into the next chapter. Okay guys, so in this chapter we are going to talk about data tree structures. So before we have explored the basics of geometry, transformation, lists, and now we are really diving into one of the most powerful aspects of Grasshopper, which is data lists. So data trees, I'm sorry. So data trees are a fundamental concept of Grasshopper, and it really allows us to manage and manipulate complex data structures. So while lists are linear, data trees are hierarchical. And this is really particularly useful when we are working on very complex parametric models, where we can group and organize data in more sophisticated ways. So understanding how to work with data trees is really crucial if you want to work with complex parametric models. And they really allow us to control how the data flows through our script in a certain ways. So let's jump right back into our script, and let's start with placing a series component like we have done so many times before, and let's connect it to a panel to see once again what it is feeding us. So here we see that all these values that we get from the series component is organized in one single list. If we were to duplicate this and go to the output and right click and select graph, you see that all of these values that we get from the series component are now divided into separate branches, and this allows us to really work with them either individually as branches, or we can work with them as a unit, depending on what kind of operation we're working with. So to show this in a more practical example, let's place a circle and give it a radius of maybe 50, and we'll divide it into points that we will use as the base points for our geometries. Let's divide it into 5 points. And then we'll connect those points as the center points for, let's say, center boxes. And we can give them a value of, let's say, 12 maybe in each direction. So here we have our boxes, 5 boxes. If we connect this to a panel, you will see that these boxes are still all organized in one single list. And if we were to move these boxes by connecting them to a move component and connect a Z unit to our translation vector and a slider of maybe 20, you can see that we are now moving all of these boxes with our slider. But if we were to duplicate our slider and connect it and set the first slider at 0, you can see that the first slider is only affecting the first item in our list, so it's affecting this box, while the second slider is affecting the rest of the boxes. However, if we were to graph this translation vector input by right-click on it and select graph and hover over the output, you see that now this is giving us 10 different geometries, and we can see that in our Rhino viewport as well. So the first slider is affecting the first set of boxes, while the second slider is affecting the second set of boxes. And this is because we have now created 2 branches of boxes. And one way to see this is we can connect our move components to a param viewer that we find here up in the menu. And here we see that we now have a component containing data with 2 branches, and every branch is containing 5 number of items of data. And if we connect it to a panel, we will also see the name of each branch and what each branch is containing. So the first branch is called 00, and it contains 4 boxes, and the second branch is called 01, and it's also containing 4 boxes. So if we were to scale these move boxes, first we need to get the center point of them by using a volume component, connect it, set the center point, and set a scaling factor with a slider from 0 to 1. We'll duplicate it, so we have two sliders, and we'll just put some random values here. And we connect our move boxes to our scale component, and we hide everything else. You see that now we are once again, with our first slider, only affecting the first item in each branch. So we are scaling only the item with the index of 0 in our branches, while the second one is affecting all of the other boxes with the index from 1 to 4. If however we were to graft this factor in the same way like we did with the move component, this slider will now start to affect the first branch, while this slider will only affect the second branch. You see? So if we were now to use a list item component, because we want to select one of the boxes like we have done before, we are now not selecting only one boxes. So we are selecting every box in every branch with the index that we put into our list item. So let's put a slider and change it, and you will see that we are always just choosing two boxes because our component contains two branches of data. So when we choose an item, we will always choose two geometries with this component. So if we want to choose only one item in a component that contains several branches of data, we need to go to our set menu here, set, and go to tree. And first we need to use a component called tree statistics and connect our boxes to that. And it needs basically an input of a data tree to analyze, and the output it's giving out is all the paths of the tree, the length of each branch in the tree, and number of paths and branches in the tree. So now we can use a component called tree item instead of using list item. And what that input needs is, it needs the tree itself, so we connect our boxes to the tree input. It needs a path, so we need to select one of the paths that we get as an output from our tree statistics component. So we'll use a list item component to choose one of the paths, and the default is set at 0, so we are now choosing the branch called 0, 0, this one, and we connect this to the data tree branch path, and the index is set at 0 as a default. So now we are choosing the box with the index of 0 in the data tree branch called 0, 0. So we are choosing this box with this component. And we can also use a component called tree branch if you want to choose the whole branch itself. And then we use the same path to the tree branch, and we connect our data tree, and we will be choosing the whole branch of items with this component. So this is a little bit about how the tree structure, data tree structure, works in Grasshopper. There are a lot of different components here that we're not going to talk so much about now, because this is a beginner's course. You just need to understand the concept of data tree structures. But for example, there are components that we use to simplify trees, and we can match two different sets of trees to have them be at the same level of complexity, so they are easier to work with. And there's one component called flip matrix, which is pretty important. So if I were to use the flip matrix on our boxes and then use a param viewer again, now you see that the difference here from the original tree structure is that now we have a collection of 5 branches, and each branch is containing 2 items, instead of having 2 branches and each branch is containing 5 items. So if I flip this and use a list item component, I will now be choosing this is a branch, this is a branch, this is a branch, this is a branch, and this is a branch. So we have kind of flipped the whole the whole structure of the data tree with this component. So when we're choosing a list item, we are still just choosing the item with the index of 0 with this component. But since we now have 5 branches, we now have 5 items with the index of 0. So we are choosing 5 boxes still, compared to when we chose 2 boxes. So this is a little bit about data tree structure, and I know it's really a lot, and it might seem very complicated at first, but once you have started to getting the grasp of this, it will really open up the doors for how to use Grasshopper in the best and most efficient ways, because whenever there's something wrong with your script, it usually has to do with the data tree structure isn't working as you want it to work. It took me a long time to understand the concept of this, so just practice it and eventually you will start to understand it, but I will probably get back to it more in later chapters. But yeah, this was all for now, and let's jump to the next chapter. Okay guys, so in this chapter we are going to dive into another crucial aspect of Grasshopper, which is mathematics. So mathematics is really at the heart of parametric design, and by integrating mathematical expressions and functions, we really are able to create very complex geometries, and we are able to manipulate geometries in very precise and customizable ways. So whether it's using simple arithmetics or if it's about applying complex trigonometric functions to generate very advanced geometries, math is really allows us to push the boundaries of the type of designs that we can create within Grasshopper. So in this episode in this chapter we will start by exploring some very basic mathematical functions and operations like addition, subtraction, multiplication, and division, and then we'll slowly move on into more advanced functions in order to construct a bit more complex curves that we can control our geometries with. So without any further ado, as I like to say, let's jump into our script. And here in our menu we have a submenu called Maths. And we have talked a bit about construct domain before. And what that does is, if we hover over it, it says create a numeric domain from 2 numeric extremes. So we need to give it a start value and an end value, and it will create a domain for us. As I said, we have talked about that before, so I'm not going to go through that a lot now. But under domain, we also have something called remap numbers, which is a very useful tool for many specific reasons. So let's say we have a random component here. Let's place a random component here and say we want 10 different values and domain from 0 to, let's say, 50. And we'll put them into a construct point to generate a bunch of points in our script, in a Rhino viewport. So here we have those points. Or let's duplicate it and we give it this another seed. Give it a value of 5, and we'll plug this into the y value, and this will be our x value. So here we have just a bunch of random points. And let's create circles on these points. And maybe we should increase our domain a bit to 100 to make it a bit larger. We'll do the same here. So now our grid is a bit larger. And then we'll select one of these points. And we'll also cool the same point by using a cool index component. And we'll plug a slider in with the value of 5, let's say. And we'll put this into the index for list item, and we'll put this into the index for cool index. So what this will do is we will choose one of the points, and we will also remove the same point in the other list. So let's hide these. And you can see now that we have chosen this point and we have removed that point from this list. So let's now create a bunch of circles on the points that are left. Let's give them a radius of 10 maybe. A bit big maybe. Let's give it a radius of 6. And let's hide this list of points. And now let's say we want to scale these circles based on how close they are to this point. And we can do that by using a distance component. And we'll use this as our A and this as our B. And here we get a list of values that the values say how close each point is to this point. So we have 9 points and we also have 9 values here. So 1 distance for each point. And now let's say we want to remap these values because we want to scale these circles based on how close they are to this point. Then we can use this component called remap numbers, which we found here under domain. And first it has 3 inputs. So we need a value to remap, we need a source domain, and we need a target domain. So the values to remap is the distance values. So we'll plug this into the input. And to get the source domain, so we need to get the domain based on this list of values. Then we can use a component called bounds, which if we hold hover over it, it says create a numeric domain which encompasses a list of numbers. So what this component does is it will automatically generate a domain based on this list of numbers. So if we hover over it, it says numeric domain between the lowest and the highest numbers in a list. So now we have domain from 14 to 92 because those are the highest and the lowest distances that we have in this list. So we'll put this into our source domain input, and then we need a target domain. So we need to construct a new domain. So let's use our construct domain component again, and let's put the sliders from 0.5 to 1 because we want to scale these circles with a value from 0.5 to a 1. And we plug, we'll set them the 0.5 into the A and the 1 into the B. So this is our target domain. And now if we put place a panel here and connect our output, our remapped numbers, you will see that we have a list now with values from 0.5 to 100. And if I drag this up, you will see that this dynamically adjusts these values to fit into our target domain. So now I can use these values to scale our circles. So I just need the center point of our circles in order to scale them. And then I'll use a scale component and I'll connect the remapped values into the factor, the center point into the C input, and our circles into the geometry that we want to scale. And I'll hide everything else. And now you see that our circles are scaled. So the closer they are to our point, the smaller they get. So let's make them even smaller. Let's make the minimum value to a 0.1, and this will be a bit clearer. And now you see that this point, that is the closest to our point, it's the one that's the smallest circle, and the further away from the point, the bigger the circle is. Okay, so this is a great component that can be used in many different type of scenarios. So let's group everything by now and hide it and jump into operators. Because I don't think there's... Yeah. So let's say we want to construct a rectangle. And we want 2 of the sides to always be 4 units longer than the other 2 sides. So we'll connect a slider into our X. First we'll just set the XY plane as the plane for the rectangle. and we'll hide this, and we'll connect a slider to the X input, and then we'll use an addition component for our Y input, and we'll connect our X slider into the A, and then we'll connect a second slider to the B, and we'll use this output as our Y. So now our Y sides will always be 4 units longer than our X sides. And this can also be used with subtraction. If we'll delete the addition, if we instead want 2 of the sides to always be 4 units shorter, then we can use the subtraction. We can increase this if we want them to be even more shorter. Or we can use a multiplication if we want it to always be, let's say, we want our Y sides to always be twice as long as our X sides. So with this we can dynamically change our rectangles, and the Y value will always be dependent on the X value. And we can always, of course, use a division component for this as well, if we want to do the opposites. Okay. So this is how we can use operators like addition, subtraction, multiplication, and division. But they can of course be used in more complex ways as well. They are used a lot in many types of scenarios. We have something here called mass addition. So let's say we have this random component generating a bunch of values for us, and we want to just add all of them together to get the result of them all added together. Then we'll use a mass addition component, and here we get output a value of all of these values added together. And this can also be done with a component called mass multiplication. So it multiplies all of the values together, and we get the results of that value, which is a huge number with this series. So yeah, let's group these and hide for now. We have talked a bit about larger than, smaller than before. So what this does is we set a value into the A, a list of values into the A, and then we will test these values against the value that we put into the B. So if these values in the A list are smaller than the value that we put into the B, we will get a true boolean for that index in the output. So if we connect the output to a panel, you will see that we get a bunch of boolean values, true or false. And if we increase this, we will get more and more true values, and if we decrease it, we will get more and more false values, because let's see these values in another panel to make it clear. Okay, so you understand how these are connected. All the values that are smaller than 27, they get a true boolean value, and then we can use these values to cull the values that are smaller. So we'll just put our output with boolean values into the culling pattern, and we'll put our values into the list to cull, and the output will only be the values that are smaller than the value that we put here into B. And this can be done with larger than as well. It works exactly the same way. We could also just invert this boolean, and what that does is all the true values, they turn to false, and all the false value, they turn to true. So that's one easier way to do it if you want to change that, but we can also use the larger than component. And we also have equality, so if the value is equal to the value that we put into B, we will get a true value. And we can also use something called similarity, where we also need to put in a percentage of how close to the B value the values that we test needs to be in order to receive a true boolean value as the output, if that makes sense. So this is a bit about those operations. Let's group everything and hide it for now. So let's jump into something a bit more complex. So let's say we generate a series of value here. Let's make the step size a bit larger to make it a bit more larger, and the number of values to maybe something like 20 as well. And we'll connect our list of values to a construct point to generate a bunch of points along the y-axis, or we can use the x-axis. Let's make this a bit smaller, by the way. I'll set it at 10. Now, if we were to use a sine component and connect our output from the series to it, it will use this data and generate an equal a list of values based on the function of the sine function, and we can use this output and put it into the y to visualize this into our Rhino viewport and connect our points into an interpolated curve to make it even clearer. And we hide the points itself, and now you see we have this this curve following this function. And this can be done with cosinus as well. Now you see we have this sine and we have the cosine curve here. And if we increase the number in our series, we will just make this list longer and longer and longer and longer and longer. And if we set this at 1, maybe it will be more clear. Yeah. So this is how we can create these types of curves in a very simple way. Okay, let's group these and hide it for now. This can also be done with something like something like a logarithm. So we'll connect our output from the series to that and connect it to y, and let's see what type of curve we get then. Not super clear in this, so let's multiply the output that we get to just make it more clear before we connect it to the y input in our point. And now we get this type of curve based on the logarithm function. So it computes the base 10 logarithm of a value. Let's group this and hide. We can also make our own functions, and now this is when it really turns interesting. So let's construct a series. We'll start with a value of 0, and maybe we'll put I think we should have a pretty low number, so let's put 0.000.5 maybe, or I think maximum can be 1 even. Let's put it somewhere like this. And the number of values we want, let's make it maybe 500. And now we plug the output of our series component into a function that we define ourselves. So we need then an expression component, and we need to set our own function here. So let's set a times x b times x So we need the x, and we don't need the y. We need a and b. And we'll connect our series output to the x, and then we'll need two sliders. For the a and the b. And we will multiply the output that we get from this expression with a sinus and a cosinus. But first we need to connect also the output that we get from the series to the sinus and the cosinus. And then we'll multiply it. And then we will use the output from the cosinus. Actually, that's to keep it clear. And then we'll use a construct point like we did before. And we'll plug the cosinus into our x and the sinus multiplied value into our y. And then we'll connect this to an interpolated curve. And now we have a curve where the radius is always exponential to the like every increase of the angle is increasing the radius exponentially. So we get this really cool looking spiraling curve that we can adjust with our sliders. So if we zoom in, you see that it's exponentially just increasing and increasing, and you can just zoom in and out. So that's pretty cool. Let's group this for now. And we can actually use the same expression for something else. But let's disconnect this, and let's put new sliders into our A and B. Not 0 maybe, but something smaller. And for this we'll use a range component. Construct domain maybe 0 to 100. Divided into, let's say, 200 steps. Put that into the X. And now we have this curve here with an exponential growth. If we adjust our sliders, you can see that we can adjust the curve itself. We can make the construct domain even larger. So this is something you can play around a lot with, and using your own functions to create really interesting curves that you can use to control your geometries with. There's another way how we can also use curves with the graph mapper. So let's copy one of the series we have created before. Maybe this one. But we'll plug this into a graph mapper. In the graph mapper you will find, where is a graph mapper? Here. So you choose the type of graph that you want by right-click on it. Let's say we want a sine graph, and then we connect our series output into here, and if you double-click, you can set a minimum value and a maximum value in the x and the y direction. So I'll set both values from -100 to 100. And then we'll construct a point based on this. So the series output will be the x value, and our graph mapper output will be the y value, and we'll connect it to an interpolated curve as well to have it nicely visualized. And we'll hide the points, and now you see we have this sinus curve that we can control with our graph mapper. So this is a really cool aspect of Grasshopper, I think, and we can try different types of graphs. Gaussian. Yeah, and you can adjust and modify these graphs with the help of the graph mapper in a bunch of different ways. And this really helps you to create very interesting organic curves that you can then later use to manipulate your geometries with. So the graph mapper is a great tool to do that. Let's group it and hide it for now. And let's try one last expression. So we'll use series again. And let's start it, or let's have the step size maybe 5 this time. And the number of values, let's make it 100. So we'll use this output to connect it to a cosinus and a sinus. And then we'll create another expression. And for this expression, we'll use something like A times sinus B times Y plus A sinus plus B plus Y C. Yeah, we need a C input as well times Y. So we'll make this A. We need B as well. Let's see. We'll need 3 sliders for the ABC. Maybe put them at 1.5. And we need to connect our series component to the Y. And then we'll need a construct point and connect this into the Z axis, while the cosinus should go to the X and the sinus to the Y. And connect it to an interpolated curve to visualize it as a curve. Hide everything else. And now we have kind of created a spiraling curve here in the Z-axis based on our sinus curve. Let's can we control? Oh yeah, we control it with the X. And now we can adjust these curves with our sliders, basically. We can make it shorter. We can make it longer. Yeah, this is great if you want to create a spiral staircase or anything else spiraling element in your designs. So that's the last example I'm going to show you guys, but yeah, we can use this expression component. This is really one of the most powerful things I believe in Grasshopper in terms of mathematics, because you can really use it for anything. So yeah, this was a bit of an introduction in how we use mathematics in Grasshopper to create and manipulate curves, and then later we can also use these curves to control our surfaces and geometries. So yeah, let's jump to the next chapter. Okay guys, so in this chapter we are going to talk about another important aspect of Grasshopper, which is vector mathematics. We have discussed vectors in earlier chapters, so some of it will be a little bit repetition, but I think it's such an important topic, so it's only good with a little bit of repetition. So vectors are fundamental in Grasshopper. They really allow us to define direction and magnitude, which are crucial when we are manipulating our geometry. So whether we are moving, rotating, scaling, or even creating very complex motion paths, vectors really give us the tools to control our operations with very high precision. So we'll explore some basic of vectors in this chapter. We're not going to cover everything, but yeah, let's jump into our script. Okay, so here is our canvas, and here is the vector submenu. So if you remember, we construct a vector in many different ways, but one is through the vector xyz component. Then we need 3 sliders in each direction, so we'll create those. Set the default to 0 from -100 to 100. And then we'll copy this 3 times, connect it to each axis. And to display our vectors, we need a vector display component. So get that. And we'll set the anchor to XY plane. And if we start adjusting these sliders, you will now see our vectors being displayed. Okay. We also can construct a vector in only one axis by using these unit components, which we have done in previous chapters, so I'm sure you're familiar with them by now. So we then connect the slider to them and control the the magnitude of that vector with our slider. We also have something called reverse vector, which does exactly what it says. It's creating a vector that is going the opposite direction of our original vector that we put into it. We can also connect a vector by referencing 2 points. So if we'll set 2 points here and reference them here, and we internalize them so we can delete our points. Let's hide this. Now we can display this, but we will set point A as the anchor point, so you will get to see the vector being displayed between these 2 points. Let's hide the points. Okay. And this is another way of constructing a vector. We can also rotate our vector. Let's say we want to rotate the first vector we created, this one. Then we need to define an axis for that operation. So we'll construct a point in the 0, 0, 0. We will move this point up in the z-axis, create a line between them, right? We'll group this and hide it, and we'll connect our axis into the x input and our vector into the v input, and we'll change this to degrees, connect a slider from 0 to 360, and connect a vector display so we can display our rotating vector. Okay, let's hide the original vector, and now as I adjust this slider you will see our vector rotating around the axis that we defined. We can also use something called X product, which creates a vector that is perpendicular to the 2 vectors that we give it. So let's say we have an X vector and a Y vector. And we copy this vector display to display our X product vector. And we hide this. You will see, first let's also display those 2. Let's drag it away a bit. Okay, we need an anchor point. Okay. So here we have the X vector and the Y vector. If we connect these to A and B, you will see that it creates a cross product vector for us. This should go here. This should go there. So it's perpendicular to this vector, resulting vector is perpendicular to both of these vectors, and it multiplies the magnitude of these vectors. So since they are, the default is set to 1, it will also generate a vector set to 1. Okay? If we were to set a slider with value of 10 to these, then this vector would go up to 100. Okay? So let's group these and hide. We also have something called dot product, and we can use the same vectors. What that does is, if we give it 2 vectors, it will give us a result of 0 if those 2 vectors are perpendicular to each other, which these 2 vectors are. So the resulting output here is 0. If we were to put this vector as the b, you would see it's not 0 anymore. Okay? So this is a great way to test if two different elements are perpendicular to each other. And I think that's about it about vectors for now. I'm sure we will have a reason to go deeper into it, but a lot of it we have already discussed, so this was just a small repetition, and a lot of it we will get into once we get into a bit more advanced scripting in Grasshopper. So let's jump to the next chapter. Okay guys, so in this chapter we are going to talk about another key aspect of Grasshopper and 3D modeling, which is meshes and sub-D surfaces. So before, when we constructed our geometries, we constructed something that we refer to in Grasshopper as a BREP, which stands for boundary representation. So we construct those geometries by using mathematical operations and using things like curves and points in order to create very precise and customizable designs. However, if we were to continue working on our geometries in something like a game engine, or if we want to render it, or if we want to 3D print it, we need to come up with a representation of that perfect geometry in order for other types of softwares and tools to be able to handle that information. Because BREPs are they require a lot of computational force in order to be worked with. So in order to do so, we need to convert them into something like a mesh. And if you are familiar with other types of 3D software, I'm sure you are also familiar with the concepts of mesh, but a mesh is basically a collection of vertices, edges, and faces. So in the real world, everything consists of building parts that consist of smaller building parts, and nothing is as perfect as a mathematical operation is. So when we want to move our objects and geometries from Grasshopper into the real world, we also need to divide them into smaller parts, which are these faces that that our meshes are consisting of. So in this chapter we'll talk a little bit about how we convert BREPs into meshes and what's important to think about. We're not going to dive too deep into it, maybe in a later video, but we'll talk about the basics and the fundamental concepts of it. And we'll also talk a little bit about sub-D surfaces and what that is. And it's a perfect tool for creating more organic and smoother geometries out of basic meshes, basically. So let's jump back into our script. So here is our Grasshopper viewport, here is our canvas. So here in our menu we have a submenu called Mesh. So let's start with just creating a very simple mesh in order to show you guys the difference between a mesh and a BREP. So this is a mesh box that needs a base box. We'll use the default by now, and it also needs the face count in each axis. So we connect a slider to these inputs, one to the X, one to the Y, and one to the Z. And as I change this, you won't really see any difference to our mesh box being made. But if I connect this to a mesh edges component, which will visualize all the edges inside of our mesh, you'll see that as I increase this, we get more and more edges and more faces in this mesh. And since this is such a basic geometry, every side of this box only really needs one face to represent it perfectly. So even if I drag this down to 1, it will still appear exactly the same in our Rhino viewport. However, if I were to remove this and replace it with a mesh sphere, this would be a bit more clear maybe to you guys. So this needs an input of a base plane and a radius. So we'll use the defaults by now and connect our slider into the number of faces around the sphere that is required in the U and the V direction. And if I connect this to mesh edges, you'll see the that these edges will increase as I increase this slider. So now it's almost like a perfect sphere. This mesh is almost a perfect representation of a sphere, and few of us will even be able to see that it's different from an actual sphere, a BREP sphere. However, if I were to decrease the number of faces to a very low number like 4, it turns into something that most of us wouldn't even consider to be a sphere. So now it's a very, very basic representation of a sphere. So when you're working with meshes, it's always important to find this balance between computational performance and visual quality. So you need to find a complexity that's complex enough for people to know what it's a representation of, but it's still easy to work with. Okay, so let's hide this for now, and let's create a very simple but organic BREP in our Rhino viewport by creating this curve. Drag it up here and change the control points a bit. Create some type of organic shape here. And yes, okay. Let's loft these. Okay, delete the curves and close this BREP. And let's reference this BREP in our Rhino viewport, Grasshopper script. And we will internalize this so we can delete this. And now there are a bunch of different ways for us to convert this BREP into a mesh. So if we go here, we will have a component called mesh BREP. So if we just connect this, we will see that it has created a mesh representation of the BREP that we created in the Rhino viewport. And we'll see this easiest by connecting the output to mesh edges. So we'll see all these faces that this mesh is consisting of. And now you see all these triangular and rectangular faces that together make up this mesh geometry, which is almost a perfect representation of the original BREP. But if we zoom in, you see that this straight line isn't going exactly as smooth as the original BREP. So it is not a perfect representation of our BREP, but it's almost perfect. You won't really be able to see the difference if you're not very, very zoomed in. Okay. So we can also control how this operation is being made by using something like a settings input into this component here. We can use something pre-made like these settings quality or settings speed, which are focused on creating a higher quality mesh. You see now it's turned a bit more complex with more faces, or one that's constructed to be faster to work with, so it will decrease the number of faces. We can also have complete control over how this is being done by using a settings custom input, and then we have to define all of these settings variables ourselves. But if we connect this now, you will see that it creates a different type of mesh that's maybe less complex than what the default settings were set at. But if we go in here and change these, we can be in complete control over how this operation is made. We can also use a triangular method by using this quad remesh method. Now it will create a mesh only consisting of rectangular faces, and the same can be done with a tri remesh, which will create a mesh only consisting of triangular faces. Okay, so there are a bunch of different ways of transferring a BREP into a mesh with these components. Let's hide this for now. We also have here a component called the Delaunay mesh. So this is a mesh that is you create a surface based on a collection of points to create this surface, or this surface is created by a bunch of different triangular faces, and the triangles are as close to equilateral as possible, which makes it very stable, and we avoid these very thin and dragged out triangular faces. And this component is especially useful if you want to create a site, for example, from a bunch of height points or typography curves. Maybe I'll make a later video on how we can use this in a very fast and simple way. But for now, it's just important to know this component exists. We also have something called Voronoi. Let's show that very quick also. Let's say we have a box here. Give it a value of 50 in each direction. And then we need a collection of points for the Voronoi component to work, so we will use a populate 3D component, use our box as the bounding box, and let's use 50 numbers, 50 points. We'll connect our box to the input here, the bounding diagram optional boundary, and here we connect our points to the point input. Now this will create a bunch of different cells around these points. Each is a closed rep. And with this we can also extract the wireframes from these reps in order to get a curve collection that we can use in a component like multipipe. And now we move into the sub-D operations. So what this multipipe does is create a branching pipe around a network of lines curves. And this is a very fun tool we can use to create very organic types of structures based on a bunch of curves or lines. Let's adjust these variables a bit. Maybe decrease the number of points to 20. Increase these. Replace the slider. Oh. Yeah, now you saw I can control how these sub-D surfaces are generated based on our collection of lines, and to create some very organic cool shapes. We can also use a sub-D component. Let's go back to the first mesh box we created, or let's recreate it. Not there. We want to connect our slider to the XYZ. And now we can use another sub-D component called sub-D from mesh, which transfers our basic mesh into a more organic, smoother version of it. So if we decrease the number of faces our mesh is consisting of, you will see that the smoothing operations of our mesh is also more and more visible. So you see it smoothens out the corner of the box. So this is how we can smoothen out meshes with a sub-D component. There's also a bunch of plugins which maybe I'll make a later video where we'll dive deeper into mesh operations and show you guys how we can work with these different plugins in order to have full control over meshes in a different type of way. Because when we're working with meshes, it's really a different type of logic that we need to apply then when we're working with reps and surfaces. So this was a little bit about just an introduction into what meshes is, how we transfer reps into meshes, and yeah, let's jump to the next chapter. Okay guys, so in this chapter we are going to talk about another very powerful and important aspect of Grasshopper, which is Galapagos. So Galapagos is a tool that is designed to help us optimize our designs. And it does so by automatically adjust a bunch of parameters in order to find the best possible solution based on specific criteria. So it operates using an evolutionary algorithm, which is inspired by a natural selection. And this means it can very efficiently search through a bunch of different options and potential solutions in order to identify the most optimal outcome. So whether we are looking to minimize cost, maximize structural efficiency, optimize our floor plans, or if we are developing some type of sunshade system using climate data, Galapagos can really help us with all these different tasks. So in this chapter we are going to talk a little bit about how it works. We are only going to talk about the basics of it in order for you to understand the fundamentals of how it works. So hopefully you'll see the potential of how you can apply it in your own projects. And hopefully also later we might be able to do a video only about Galapagos and apply it into more real architectural projects, for example. So without any more talking, let's jump into our script. And in this example that I'm going to show you guys, let's start with just constructing a simple rectangle. And we want it to be constructed in the XY plane. We can hide this and connect it to the plane. And for X, let's say we want 200 units. And for Y, maybe 100 units. So here is our rectangle. Now let's explode this rectangle. So in this example, I want to use Galapagos in order to manipulate our geometry after specific criteria that I give it, in order to give you a very basic but still a bit complex example that would take, it would be very time consuming if we had to do it in traditional CAD. So I'll show you a bit about the potentials of Galapagos with this example. So I'll start off with exploding this into its segments. And I want to choose the long sides, so I'll use a cool pattern and set as multiple boolean to true false, because I know they are sorted long, short, the sides. So here I have the long sides. Then I'll use a point on curve component. Use an interpolated curve between those 2 points. So I get, actually, no. Let's instead use a list item and choose each side individually, so we have more control over each curve, because we need to flip one of them for this to work. So we choose this with the index of 0, and then this will be the index of 2. And then we'll use a component called evaluate curve. So what this needs is an input, the curve to evaluate, and it needs a parameter on curve domain to evaluate. But first we actually have to reparameterize these curves. So we'll plug them into a container, we right click on it, click reparameterize. We'll do this on both of them. We can hide these. And for this it needs a slider from 0 to 1, and it will it's basically doing the same thing as the point on curve component, but it does so with sliders, which we will need later on when we connect it to Galapagos. So now as I change this slider, you will see that this point is changing as well. And I'll connect this to this as well, but since this has a different direction, you see it does not really do what I want. So I need to flip this curve with the flip curve component before I connect it to my evaluate curve. Actually, I'll connect the item to flip and then the flipped curve to reparameterize. And now as I change this, you will see that they are aligned in the same point in the X direction, which is exactly what I want. So now I can hide these two, and now I can use an interpolated curve and connect both of these points. So now as this slider adjusts, my curve that is going to cut this surface up in two is also adjusting. Okay, now I want to do the same thing but split up one of these two curves into one of these two geometries that are being created now into two new surfaces. And I'm gonna make this into a surface. That's why I'm calling them surfaces. Okay. So I'll use the same type of idea as I did here. I first need to reparameterize this curve and use an evaluate curve component. Okay, now it's doing exactly the same thing, and I also want this to be done on this curve. So I need to choose this from the explode component I used before with the list item component, and let's change this to, I think it should be index 1, yes. Okay, and I will do the same with this. Reparameterize it, connect it to an evaluate curve. And now you see they are aligned in the y direction. So I can use an interpolated curve on these two points in order to create my curve. So now I have these two curves that are adjusted with two parameters. So now let's first make it a bit more complicated for Galapagos to solve this issue. Let's split this surface up. Let's cut out some holes in it. Otherwise it would be very easy for Galapagos to just figure out what I want to do. And what I want to do is to split this curve into one piece that is the largest piece, and that should be twice as large as the second largest piece, and the second largest piece should be twice as large as the third largest piece. Okay, so this is my whole assignment for Galapagos with this specific project or example. But first let's split this surface up by using some circles. So I'll first reparameterize this surface so I can use a multi-dimensional slider on it in order to choose my locations for the circles that I want to split it with. So I'll also need an evaluate surface component for this, and I'll plug this UV coordinate that I get from the MD slider into the UV input and my surface into the surface input. So as I move this around, it moves around this point that I want. And let's make 3 different ones. Let's have 3 circles for this example and have them at different locations. And now let's use a circle component and use these points output as my base plane of circle. And radius, let's connect 3 sliders so I can connect, adjust each one of them separately. Maybe this should be big, this should be a bit smaller, and this should be this maybe. Okay, and now I'll use a surface split component, which needs a surface and it needs a bunch of splitting curves. So I'll use my circles as a splitting curves and connect the surface into the surface input. And then I'll choose the surface that is the big one. So this is the one that I want to split up with my curves that I created up here, okay? So for that, I actually need another surface split component. So I can duplicate this, connect this surface into the surface input, connect my curves here. Let's merge them into a curve container first, make it a bit more clear. Connect this to the splitting curves. And now it has splitted this curve surface into 3 surfaces. And that is exactly what I want. So if I hide these curves, you see now this is a surface, this is a surface, and this is a surface. Okay, so now I need to now I need to choose these surfaces in the right order. So even if changes are being made to the sliders, which will happen when I connect it to Galapagos later, I need some kind of logic that allows me to always choose the surfaces in the right order. So I'll use an area component on these and deconstruct the center point and sort these surfaces based on the x value, because I want to choose this surface first. This is my biggest surface, the one that has the lowest x value, because it's closest to 0 in the x-axis, because this is x-axis, okay? So I'll sort my surfaces based on the center point the center point of the curve's x value. So I'll plug the x into the k, I'll plug my surfaces into the a, and then I'll choose a list item, and now it will choose this surface when I connect the a into the list. Okay. And now I can group these like a blob, change the color, and I'll also use a cool index with the same index, the 0, to get my 2 remaining surfaces, and then I'll use the same thing with these. I'll do the same thing with these. But now I want to instead sort them based on the center point's y value, because now I want to choose this first. So I'll connect the y to the k, these 2 surfaces to the a input here. But since it sorts based on the lowest value first, I actually need to reverse this output that I get from the a, because now I want to choose the surface with the highest y value, okay? And then I want to choose the one with the lowest, so I can have one with the reversed order and one with the real order. So now my surfaces, if I merge them here, first the biggest that I want to be the biggest, then the one I want to be second biggest, and the one I want to be third biggest. I can hide everything here. Group these, blob it, change the color just for fun. And now I have my surfaces here in the order that I want them. So what I need to do now is to calculate the areas of these. And you will understand why in a little bit, okay? As soon as I start using the Galapagos components, you will start to understand why I'm doing all this. Hopefully. So here I have a list with all the areas. And I want, as I said before, I want this to be twice as large as this, and this to be twice as large as this. So what I can do first is to cool index on these values, but reverse this list, because the smallest, this one's area is not something I'm gonna test against something else. I'm gonna test this one's area towards this, but this one I'm not gonna test against anything. So I can actually remove this from this calculation part by cooling it, first reversing the list, cooling the one with the index 0, and then calling back the list so that I still have them in the order largest to second largest. And then I can also use a shift list with the value of 1, or I'm using the shift list on the areas, of course, and I'll set this to false. Okay, so these are now this and this. I could have made maybe the same component. Anyway, now I will divide these values into 2. And subtract it with these values. And if I get minus as a value, I need to use a component called absolute, which turns all negative values to positive values. Okay? Because I only need to know the difference between these values and these values. So these values are the areas divided into 2 that I'm testing against, and these are the values I'm testing, if that makes sense. I know it can be a bit complicated, maybe, if you're not used to this, but hopefully you will understand in a minute when I start connecting everything to Galapagos and show you how it's done. I'll also use a mass addition component because I only want one value, and I want this value to be as close to 0 as possible. Because if these are if this were twice as big as this and this were twice as big as this, then this value should be 0, 0, which it's not now. Okay. What I also want is I don't want more than 3 surfaces being created, and this is very, very important. So I want the list of splitted surfaces to be 3. So if I use a list length component and divide this value with 3, subtract, I mean, set 3 here, I get a 0 value because now I have 3 surfaces. But if the simulation later on would make a change to these curves and create more than 3 surfaces, then this value would increase. And then I can actually connect this to a multiplication to emphasize how important it is that I want it to be three surfaces. So I'll use maybe multiply by 100 component and connect this to my mass addition component. And this will be my fitness value that I later on, or that I give to Galapagos in order to, and I will tell Galapagos to minimize this value. Do what you can to minimize this value, because I want the number of surfaces to be 3, and I want this to be twice as big as this and this to be twice as big as this. If that was the case, then this value would be close to, it would be 0. Now it's not, so now this value is 3700 something. But by changing these sliders, the goal is to get this number down to 0, if that makes sense. So now I just need to connect everything to Galapagos. So Galapagos you find in the first submenu, and this component is called Galapagos. The difference with Galapagos from other components that we talked about is you actually drag from the Galapagos to the input that you want. You don't drag from the input to Galapagos. It doesn't work. So you need to drag from Galapagos to the input. So if I hover over these two values, it says genetic input and a fitness input. So the fitness input is this value that we can tell Galapagos to either minimize or maximize. I want this number minimized. I want this to go down to 0. So I connect my fitness into this value from my mass addition component. And for this gene input, genetic input, we need a gene pool. And a gene pool is basically a bunch of sliders. So if I double click, I almost get the same settings as for a normal slider. I can change first how many I want, and in this specific example I only need 2 sliders, so I'll change this gene count to 2. And let's use as many decimals as possible, because I want it to be precise. And I want the minimum to be 0.01, the maximum to be 0.99. Because now I'm gonna replace these 2 sliders I made before with these Galapagos gene pool values. So I'll first split them into 2 lists by using a list item, reverse one of them. So now one of the outputs is this value and one is this value. And I will connect this to the parameters input in my evaluate curve surface and replace this slider. And then with the other I will replace this slider. So what Galapagos now will do is to try all these different potential solutions. It will try every single one of these values in order to minimize this value as close to 0 as possible, okay? And when it has done so, that means that my goal has been achieved. If I were to create more or less than 3 surfaces. So now you see we only have 2 surfaces here. Then the list, this thing that I did, will give a value of, wait, I need to put an absolute here first. It's a good thing I tried that. Then you get a value here of -1, which this absolute turns into 1, and then because I multiply it with 100, it will give an output of 100, and add that to my mass addition value. And actually I can make this 1000 just to show this is not something I want. It's very important I keep it at 3 surfaces. And now how Galapagos works is, first it just starts with a bunch of random numbers. Then when it sees that the number that performs best according to my target, which is to get this minimized, then it will use those values and create a bunch of new random values close to that value, and then slowly it will get closer and closer and closer to the optimal input for these two values in order to get this value down to 0. And I'm sorry if it sounds complicated, but let's now start this. First I have to connect my gene to my gene pool. Then I'll double click here. Here I changed what's my goal with this. I want to minimize my fitness value, so I'll put this to minimize. I can use a population of maybe 400, and initial boost I increase to 4. And I'll leave the others at default. Go to solver, check this in order to see all the different solutions while it's working on them. But before I start it, let's also connect an area to these, and use a text tag so I can see, or so we can see how the changes are being made in real time. So I'll set the center for the location of it, the value of the area as the text. So now I see what area each of these surfaces have, okay? And that's it, I think. Let's now start the solver. Go to solver, again check this in order to see all the different genomes in the Rhino viewport. And I'll click start. And now it starts working here, trying all these bunch of different options. And this can take some time. Hopefully, if I've done everything correct, it will find where the perfect location for these two curves that I created is, in order to get this surface twice as big as this and this twice as big as this. Yeah, so now all we do is wait, basically, and let it do its thing. So we see here it starts off with just a bunch of different random inputs all over the place. But then slowly as it progresses, we will see it's getting closer and closer and closer to what it is we want to achieve. And here we can see the fitness value that is currently the smallest that it has been able to find. So right now it's 94. But we want this value to go down to 0. Oh, now it's 28. So you see it's making real progress real quick. And you can also see that now in our Rhino viewport that it's starting to get closer to some type of solution here. And the changes is getting smaller and smaller between each sets of attempts or trials. Now it's down to 12, so it's doing really well so far. Maybe not the most complex task for it. We probably could do this in Grasshopper ourselves, but I just wanted to have a pretty simple and basic example for you to just understand how it's working. But as I said, hopefully later on we will be able to, I can make maybe a video where we use this in a more complex setting in order to use climate data in order to optimize our architectural designs and make them as sustainable as possible, using the position of the sun or using things like solar radiation measurements, and so on and so on. So now you can see it's almost down to 0 already. Yeah, it's probably not gonna need much more time, but we'll let it work until it's finished. Okay, let's stop it for now. You can see it's basically down to 0. These are square meters now, so it's 0 square meters. We can stop it for now, but if we would let it go, it would probably continue until 0.000 maybe. But that's not really that important for now. But you can see how we can use this tool in order to achieve anything that we ask it to. So this example was not too complex, but hopefully you got an understanding of how the tool can be used and how it functions and works. So with that said, let's jump to the next chapter. Okay guys, so in this last chapter I thought we would try to use some of the techniques and methods that we've talked about in previous chapters and apply it in some more practical examples. So I'm just gonna jump right into our script. I haven't really practiced this chapter, so it's gonna be a bit of an improvisation, but I'll try to remember as much of the things that we've discussed in previous chapters and just try to apply it in different ways, so you can see, hopefully get some inspiration on how you can apply it in your own design challenges. So let's start with just constructing a circle in the XY plane. And let's create some type of architectural building first. So let's give it a radius of maybe 16. And then we want to move this up in the z-axis. Let's move it maybe 5 meters. So this floor will be a bit taller than the rest of the floors, but this is the entrance floor, so to create some kind of entrance situation here. And let's then offset this curve. Not with this, but with offsets. This one. Okay. Let's offset it with maybe 2 meters. Let's group these. So this is the first floor group. And with this one, we can start constructing our floor plans. So let's start with moving them up in the z-axis with a series component. And with the series component, we want the starting value to be 0. We want the step size to be something like 3.4 maybe. This is the floor height. And we want the number of floors to be maybe a value of, not 20, 5. We connect it to the z-axis, to the unit, and then this to the translation vector. So now we have our floors here. So I passed by this circular building the other day, so I'm trying to create some type of version of that, or at least my interpretation of that building. with this example. So we did this before with connecting a series component to the move, and then we're going to connect this to let's first group this, and then we connect it to a rotation component. We could use rotate an object in a plane, but let's use rotation through around an axis instead, so we get that, because that's what we will probably use most of the times. So we need to define our axis by getting the center point from our circles with an area component, move this center point in the Z axis with our move component, create a line between these two. This line will be our axis, so we connect the output to the X input here. Change this to degree, and then we need our series duplicated. But for this, let's set the step size to something like 20, or let's set it at 0 for now. And we're going to group this and connect the series to the degree input and the move to the geometry. And we can hide these. Okay. Now let's also use a scale component. So we're connecting the center of the circles into the center input, the rotation output into the geometry input in the scale component, and then we need our series again, but this time we want the starting value to be 1, because we want the first curve to be scaled with 1, a value of 1. And we want the step size to be a quite low number, so we're going to make a slider from 0 to 0.2. Maybe set it at 0.03 maybe. Okay. We can hide this and make a group out of this. And now let's create our floors by extrude this curve. The value of maybe 0.2. And let's close this with the cap component, so they are closed preps. And then let's also move our curves with this value in the Z axis to create some type of ceiling as well. And this we have to extrude with a negative value. Maybe we're going to use the same, so we'll just use the negative component here and connect this Z output to this to extrude these, and then we're going to cap them as well. So now we have 2 breps here. Let's make 2 brep containers, one for floor, one for ceilings. Let's group this, hide it. And these we can actually connect to a custom preview with a color swatch, because later on we won't, it's going to be hard to see what it is we're working on when everything is red. So let's set a color for these, group it. Maybe not white, maybe some darker shade. Let's use the same color. Okay, group this. Okay, so here we have our floors and ceilings. Now we want to create our facades. or first let's create some balconies for these floors. And let's create some balconies by using curves that organically move in towards the center and creates this space for balconies. So let's first move up our curves so they are aligned with our floors. So we need to use the same value as we did here to extrude them. And now they are aligned. Okay, perfect. Let's drag this down here. So now we're starting on the facade part, or the balconies. Okay, let's divide these. Maybe 10 is good. Let's see. Yeah, let's use the default value of 10. And then let's shatter these curves. I don't know if we have talked about the shatter component before, but what it does is it splits curves based on these parameter values that we get from the divide component. So we're going to connect this to the T input and our curves into the curve input, but we have to graft our curves, because you see here these are organized in a data tree structure, which these aren't. So let's graft these, and now it has splitted these curves. So we have 5 branches of data. Each branch has 10 number of items. So each floor is a branch, and each of these curves is an item in those branches. Okay. So let's use some cool pattern component here with a culling pattern of, let's say, false, true, false, and make it multi-line. And let's see how this looks. Okay, but this looks good. We get 3 balconies on each floor, perfect. But maybe we don't want the balconies to be aligned like this, so let's increase our rotation a bit. Get them a bit more randomly placed. Okay, perfect. Okay. So we're also gonna duplicate this culling pattern and invert this pattern and save this for later. We can hide everything else. Now let's use these curves that will be our balconies to divide them into points. Maybe 5. Then we get 6 points on each curve. Okay, and let's move these up in the Z axis in order to create a line that we can use as an axis to rotate this vector. Okay, we have done this in previous chapters as well, but this is a bit of repetition. Let's hide group and hide these and use a rotate vector component. Connect the line into the X input, change this to degree. Think it was 90, could be 270, so let's make a slider from 90 to 270. And connect this, connect the tangent vectors into this. Now we need to multiply these values, and we want to multiply these with sliders. And we need 3 sliders, 1 slider affecting this and this, 1 affecting this and this, and 1 affecting this and this. Okay, so let's place a multiplication component, and let's do a merge here with our 5 sliders, 3 sliders. So this goes into this. We can increase the number of inputs here by just clicking the plus button. So we want 6, we have 6 points, so we need 6 inputs. So this will control the first and the last point, this will control the second and the second last point, and this will control the central 2 points. Okay, connect this to the multiplication component and connect the vector output from the rotation vector component into the A. And now let's move our points with this output. Let's hide everything. So if we move this, you see these points are moving a bit. Maybe we don't want to move them that much. these we want to move to 3 meters. Let's connect these to an interpolated curve so we see how the curve is being constructed based on these points. Okay, but that looks pretty good. Maybe a bit less. Okay, but this will do. Now let's join these curves with the ones that we left over here, the ones that we didn't manipulate. Let's flatten this so we get 5 closed planar curves, and these will be our facade lines. Okay, let's divide these curves by length, but only to use and divide. Maybe 1 meter. But we're only going to use the number of points with the list length component. And then use a divide by numbers, divide curve. So we get each of these lines equally long with 1 meter as a reference. So they will be almost 1 meter. Yeah. We need to graph these curves because you see this is in a data tree structure, which these are not. Okay, perfect. Now let's create an interpolated curve based on these points with the degree of 1, because we want them straight, these lines. So now each curve here between the curves are straight, because that's how you would do in a real construction. Okay, now let's explode these and cull with a pattern of true false. So we split them into what? True, false, commit changes. Okay. And we're gonna duplicate this and invert this. Did I set this to true? No. Okay. I'll set this to true as well. Okay. Okay. So now let's create some type of facade panels. Facade panels by extruding these in the Z direction. Let's control these manually because I'm not sure how. We could use a subtraction for that as well, but I think this is just faster right now. Do it manually. Something like that. Looks about right. Three meters, okay. Let's offset these. Not with the negative value, we want them inwards, maybe 0.2. But now if we want an extrusion based on these, we want a closed prep between these two, then we can use something like a vector 2 points. So first we'll get the center point on these curves, surfaces, Then we'll use a vector 2 points. Use this center point as A, this as B, and then we can extrude the original surface with this direction. And now we will get closed preps. These panels will be closed preps. So let's put them in a container. Hide these. Drag this here. Duplicate this. So maybe this will be a bit reddish, something like this. Okay. Perfect. So now let's take these that we didn't do anything with, other curves, and create some sort of windows with these. First, let's maybe move them in the Z, something like 0.4. Ruled surface between these. Offset these curves, something like 0.1. Minus 0.1. Okay, and let's move them again. Ruled surface between those and those. Wait. Let's flatten them out. Okay, they're not going to be that tall, maybe 0.2 maybe. Okay, cool. Let's put these in a rep container. And set the color to them, group them, hide this. Maybe it looks a bit weird. Let's decrease this to 0.6 maybe. Yeah, that looks a bit better. Okay, let's now yeah, the windows. So we have these curves. Let's move them up. Create a ruled surface between these. Flatten once again. Okay. And let's make them a bit bluish. Okay, let's say if we want to make some kind of railing for these balconies. So we are going back to so these are the curves. Let's use a shader on these curves. First, let's parameterize them. Always have to do this before you use a shader component. or evaluate curve, or evaluate surface. And then we can use a slider from 0 to 1 and use a subtraction component where we use 1 as the A and our slider as the B. So now we will cut this in 2 parts, so we can control which part of this curve we want to use for a railing. And let's set this to 1 to choose the middle curve. Okay, you see this curve now? We can control with this slider how long it is. So we'll use something like this. We can hide this. Let's offset this curve with some value of don't really know. Let's see. Okay, we're gonna use a negative value. Minus 0.2. Let's use a ruled surface between these. Actually want it to go out all that way. Okay. Now let's extrude. Let's drag the railing down here. Extrude this railing base. Something like this. Okay, then we'll use a tween curve between the offsetted curve and the curve we chose in order to get this middle curve. We can move this up the same value we extruded our base with. And then we can divide this by length. Maybe something like 5 centimeters. Maybe 10. And then we're gonna move this up a meter. Create a line between these two and pipe this line to maybe a value of 1 centimeter. Maybe that's too small. No, that's okay. The radius value. Okay, and let's also move our base up, or no, let's move this surface up. But we need to add this value with this value and use that as our Z translation vector. And then we can extrude this as well with a value of maybe 10 centimeters. Okay, so let's now create a container for all of these. They will have to have the same colors. Let's group this. I'm gonna drag this up here and give it a color and group it. Now we can hide everything here. So now we have some railing to our balconies. Probably should shorten this curve a bit. looks a bit weird. Something like this, maybe even 16. Okay. So perfect. So here we have our circular building. We also need to do this ground floor plane. So let's see here. Okay, we're just gonna duplicate these down here and use our circle instead. Let's connect this circle to a container and drag it down. We might have to make some changes to the z values for this to work, but I think it's still faster, this method. Okay, so this is an extrusion, this is a ruled surface, this is a ruled surface, this is a ruled surface. Okay, those are into a rep. Okay, so let's connect these to the same colors first. So this should go into the panels rep. You can hide this. This should go into this one, I believe. And our glass should go into this one. But now we need to just adjust these heights. So this needs to go way up 5 meters, and these should go something like 5 meters almost as well. And maybe we want these to be a bit longer in between them, so we're gonna set this to maybe twice as big, 1.2 meters. Okay. So here we have our little building. Now, the great thing about working in a parametric way is that we can adjust each little detail and every aspect of this model with just a simple change in a slider. And we can also use, if we want to create more detailed windows, or if we want to create doors here or change anything in this model, we can also just find where we can reference that part of the model and then continue working on it in a separate part of the script. So also, if we were to say, let's make this a skyscraper instead, let's make this 30 floors tall building instead, we can just set this slider to 30, and it's gonna take a little bit of time because it has to calculate all these components, but now we have made a really tall building with the same type of logic. We could also do something like let's say we want to scale this, but instead use something like a graph mapper to scale this, and use maybe a sinus curve. Scale it with the function of a sinus curve. So we're just going to connect our series to this, change these values to maybe from 1 to 1.5. So these are the values we will scale our circles with. And then let's see what happens when we connect this to the scaling factor. Okay. And now we can adjust how these floors are scaled with this slider. We want to create something like this. And let's enable this now, see how it looks with all the different components. Oh, I forgot. It's gonna need a bit more time. So now here we have our sinus tower. So this was just some experimenting with some of the functions and things that we have talked about in previous chapters. So I hope it gave you some inspiration on how you can work with these tools in your own design projects. And I want to thank you for watching this tutorial, and I hope to see you soon in more videos. I would love to make videos and show you some of the plugins that Grasshopper has. And yeah, see you next time. Thank you for watching.